This is my second time to Poland and my first time speaking at Lambda Days. I absolutely love this place. Actually, I do. So yeah, I'm glad I'm here. I'm glad you guys invited me over. And hopefully we can have a very introductory talk about quantum computing, set some context around what it is and how it works, what it's good for, and then maybe dive a little bit into some of the innovation that's happened over the last few years, of which I have played a very small role. My name is John Azariah. I'm the principal architect at Microsoft Quantum. We are building a full stack quantum computer, and you can follow me on Twitter if you like. So, what is the buzz about quantum? Why do we care? Where is the stuff going to be used? Do you need to learn it now? Will this be something that everybody will use every day of their lives? How do you get started? What are the building blocks? And how do you actually get moving? What are the tools available? That's really what this talk is going to be about. This is a very introductory level talk. If you start asking me deep questions about condensed matter physics somewhere halfway in the middle of the talk, we will go down a couple of very interesting rabbit holes. So I will table those conversations for later. All right? Cool. So we've been doing computing for some time now. Started a few thousand years ago. We've had different mechanisms for doing different types of computing. Back in the day, we had beads and wires, and people used that for basically doing accounting. Probably more familiar to all of us is the stuff that is sort of in the middle, right? We went to having semiconductors, we went to having digital logic, and we're all here because this is what we do on a daily basis. We use this stuff, right? How different is what we're doing now from the beads and wires? I'm actually going to make a fairly bold claim by saying that it's not all that different, actually. So if you think about the operations that you're dealing with, the basic arithmetic that used to be possible with, say, an abacus, we've kind of distilled out and abstracted away some of the detail of math to get to Boolean logic, and then built effectively the abacus on the digital system. It's obviously a heck of a lot faster, but we can do more in the same kind of arena. If you think about the difference in scale, there's a huge leap between what you used to be able to do manually and what you can do with a computer these days. I want you to imagine that kind of leap between what you can do today and the kind of stuff that quantum computing is going to be able to allow you to do in the future. Now, obviously, that sounds a bit hypish. I want to downplay the hype a bit because I'm not in marketing. But I do want to tell you that the differences are actually very profound. To give you an example of that, here's a little problem. That's an RSA 2048-bit challenge. If you could have factored that number into its constituent primes a few months ago, maybe last year, you would have been richer by $700,000. There's a reason why that thing is hard. We depend on it being hard to do with the mathematical tools that we have, because that is the problem that keeps your bank account safe, right? So if it were easy to factor such numbers, the economy system that we have right now would actually be under threat. We would have a hard time keeping any secrets at all. In fact, you can take some time trying to solve that problem. But what the quantum machine can actually provably do is, with a reasonable type of machine, reasonable quantum machine, you could actually solve that in about a minute and a half. And to think about the kind of scale difference that we talked about between an abacus and the standard CPU, that's kind of the scale difference that you're talking about between 1 billion years and 100 seconds. And this isn't the only problem that the quantum machines are going to be able to solve. Now, why is this the case? Is this a matter of Moore's law just getting better? Right? If you took machines that were basically in the 2003 time frame, you couldn't even hit the curve. So for RSA 2000-bit challenge, you could take a classical cluster of machines that were built in the 2003 time frame and would be beyond 1 billion years. Moore's law basically gives us that. You move the curve a little bit to the right, and in 2018, we can crack 1 billion years, no problem. Right? But the idea behind the quantum system is not about moving the curve further to the right. It's about changing the shape of the curve entirely. It's about making it look like that. And the reason why this is possible turns out to be very interesting. It also turns out to be fairly niche. There are only a few problems that we know of that actually have a quantum advantage now, but this is one of them. And if we get to the point where we have a 1 gigahertz cycle quantum machine, this would actually take about 1.5 minutes to solve. So the idea that I want you to get out of this first is that this is a paradigm shift in how we do computing. It's a paradigm shift in how we actually think. What does it mean to compute? And what do we use to compute? And part of that is what I'm going to cover in the rest of this talk. So this is the fastest supercomputer in the world at the moment. It's currently in the US. It knows how to analyze the ground state of my favorite molecule. So what does it mean to analyze the ground state of this molecule? It means that we fully understand how every electron in every atom interacts with every other electron. And now we can actually predict what shape the molecule will look like, what kind of reactive properties it will have, all by looking at the math behind how you model the electrons and how they interact with each other, right? This molecule is another favorite one. It's very important to humanity, as it turns out. And this computer will not be able to crack it within the lifetime of this known universe. That is the Femoko molecule, and I'm about to give you a little bit of a story about that. So walk with me back to 1911, I think, just before World War I, where we were pre-industrialized farming. We didn't actually use mechanical fertilizers. We didn't use mechanical farming. We basically didn't have fertilizers. And we basically needed a way to grow crops. So the main fertilizer that was actually used turned out to be something which was derivative of ammonia. And ammonia is very difficult to make. So there were two gentlemen from Germany who came up with the Bosch-Haber process, which is actually virtually unchanged even today. We still use exactly the same process. It's an extremely power-hungry process. Between 2 to 3% of human energy output actually goes towards making ammonia for fertilizer. So the chances are that everything you have ever eaten in your entire life has depended on the Bosch process. Now, why is this molecule interesting? It's because before the Bosch process, if you wanted to make a field fertile, you grew beans in it. And in the root of the bean plant, which is over there, you find parasitic nodules. And in those nodules, you will find some bacteria. And those bacteria know how to convert atmospheric nitrogen and hydrogen from water to ammonia at room temperature and atmospheric pressure. Very far cry from the kind of high pressure, high temperature requirements of the Bosch-Haber process. That molecule is the enzyme that makes that happen. And the interesting bit about that molecule is the Femoko bit in the middle. And we don't have an ability to understand why it works. Because in order for us to actually compute the ground state of that molecule, you will need more bytes than there are atoms on this planet. So you'll never get a computer with the classical capabilities to be able to do the same kind of computation as we did for the caffeine molecule for this molecule. But nature doesn't seem to have this problem, right? Nobody told the bean plant that, hey, this is a computationally difficult problem. How are you going to actually do this? Nature seems to have some way of actually figuring it out. And that's the key here. The key is to actually take the behavior of quantum mechanical phenomena that are taking place at the atomic scale in nature and use them to actually do your computation. So if you think about it, I made a statement that the math was too difficult to be able to solve this natural problem. Another way to say it is that nature can solve really, really difficult problems quite easily. And so if you can somehow reframe your problem in terms of how nature actually represents the issue, then all of a sudden you actually can use quantum mechanical phenomena as a computation device. That's the fundamental difference between how we change what the meaning of computation is. Okay? So what does developing quantum algorithm look like? Well, first you find the algorithm. You figure out that it actually is better to do it with a quantum machine than it is with a classical machine. And that itself takes a little bit of mathematics. Then you confirm that it actually is truly a speedup. And you can do that by actually, so Professor Peter Shor did this to get the integer factorization problem solved. And every algorithm that we know of, and we only know of a few dozen of them, actually goes through this process of actually figuring out whether the algorithm does actually have an improvement once you apply a quantum speed up on it. And then of course you optimize the heck out of it, and then you embed it into the quantum hardware and run it to get a solution. And we did this with the Femoco molecule. We used a special simulator that didn't actually do the math, but counted the kind of operations that we would have done. And the Femoco simulation, which went from several billion years, after we wrote the thing down using quantum mechanics and ran the algorithm, we brought it down somewhat. We hit it about 30,000 years, which is an improvement, but it's not a particularly useful one, right? So this is where the whole idea of using all the tools that we can bring to the game becomes important. So by providing all of the standard known optimizations, we could actually bring this whole thing down to a computation that would take 1.4 days if we had a 10 nanosecond gate. And we can do all of this even before we have the first qubit, because we understand the math, we're just not capable enough to do the math. We know what kind of operations we need to do, so all we have to do is profile the algorithm and work with it. And if we have sufficient tools to do that, then we can actually get improvements, and we can come up with algorithms that we can know will work when a quantum machine is able to run. And so this is a key important position we're in right now. Nobody has a quantum machine that will even run the 1.4 day problem. A quantum gate that's there right now won't even hold its state for a second, or even 100th of a second. But we can still research about this using some of the tools that we know about. And if we can build enough interesting little tools to do that, then we can actually make progress on the algorithm side while waiting for the physicists to come up with the device. And that's currently what the state of the art is. So let me show you a little bit of the wild and weird world of quantum information. So who recognizes that? Everybody. Okay. What were you told is, so basically, well, we recognize mathematicians and functional programmers here, and then there are some people who've actually done things a little bit lower down the stack, right? So a NOT gate is probably about as simple as it's going to get. And you can kind of say, okay, I can represent 0 by the presence of a current or the absence of, or an absence of 1, 0 and 1 that way, or the presence or absence of charge, or the presence or absence of some kind of magnetic thing. And the NOT gate is something that actually takes a 0 to a 1 or a 1 to a 0, right? But what if I told you that all those abstractions that you talked about just now were kind of a sugar-coated lie? And really what's happening underneath is a more fundamental mathematics. So let's say that I represent a bit as a vector that way, right? And now, what is a NOT gate? What takes the 0 vector to 1 and a 1 to a 0? Well, it's some kind of matrix, isn't it? It's some kind of matrix that does this kind of thing, right? So if I take that matrix and I multiply 0, I get a 1. And if I take the same matrix and multiply 1, I get back a 0. Now, this actually has no, it's truly an abstraction because we don't know anything about how we represent any of these things. But there's a mathematical way of representing the operation that takes you from one place to the next. And we can now work out the full-blown math for the NAND gate. And once we do that, then we have a provably complete way of representing any n-bit algorithm. Yeah? Okay, so let's figure out what to do with 2 bits. How do we handle 2 bits? I'm going to introduce this operation called a tensor operation. And what that does is it actually converts 2 vectors of depth 2 to a vector of depth 4. And if you think about that, you see, kind of squint a little bit, it's 0 tensored with 0. And if you look all the way to the right, it's still 0. The 0th bit is 1, and everything else is 0. So the math kind of works. And if you tensor 3 bits, well, the vector on the right starts looking a bit big, right? And this should give you some intuition that there's something more fundamental going on than multiplying 0 times 0 times 0. Because this vector on the right encodes how big your 0 is, how many bits of 0 there are in some sense. So, of course, being mathematicians, we have shortcuts of doing things. So we have this Dirac notation, which basically just represents each of these binary vectors literally as the binary bit string. So this should not be very different to you. But I'm going to make things a little bit more interesting now. So you've seen zeros and ones. I'm going to introduce complex numbers. I'm going to tell you that a bit is actually that. So the 0 bit that you know of is actually a vector of 2 complex numbers, not 2 plain old numbers. And the 2 complex numbers happen to lie on the real line. And so all that you're doing so far is saying, okay, I now know that there are 2 points on the real line. I know a matrix multiplication that can flip them, right? And I'm going to do something with that. So if I add the complex piece to it, then I kind of expand my horizons a little. And in fact, to represent the state of a single bit now, I can use a 4-dimensional sphere, if you want to think of it like that, to represent the north and where the north and south poles are actually the real line. There's no imaginary component to this axis, and 0 and 1 are effectively the north and south pole of that sphere. And now if you squint a little, you can see that virtually all of classical computation is operations on just the north and south pole of a given sphere. So what if that sphere, every point on the sphere could participate in your mathematics? What would that give you? And as it turns out, once you take every point on the sphere and allow it to represent the state of the thing that you're using as a computational basis, you come up with a qubit. So a qubit is effectively the same kind of vector, except that instead of 0 and 1, we have two other complex numbers which lie on the skin of that sphere. And now, because it's on the skin of that sphere, its amplitude must be 1. And every point on that sphere is now a complex number. So in order for you to do any computation on that sphere, you can represent that as a series of rotations. If you think about me having a big beach ball over here, and I started with a dot on the North Pole, I could take that dot to anywhere on the surface of the sphere by just rotating it. So every operation that happens on a qubit can be represented as exactly that. It can be represented exactly as a single rotation or a series of well-known small rotations. Specifically, the NOT gate is exactly the same as we had before. And so now you should get a sense that really the whole of classical computation is in some sense a special case of quantum computation, where the only points that you can sort of operate on are the two poles of the sphere. But the quantumness of it allows you to basically take any point on the sphere and do stuff with it. Of course, there's a caveat, right? The caveat is that when you try to actually look at the sphere and ask, where is the dot? The sphere will not tell you. The sphere will only tell you probabilistically, I'm at the North Pole or I'm at the South Pole. So from the pop culture reference of it is when you observe this qubit now, it collapses to one of its two classical states. And that's really what it means. So, for example, here are some of the other rotations that can operate on it. And here is a special operation called the Hadamard gate, which effectively takes a point from the North Pole to the equator. And now when you ask the sphere, where is the dot? It's going to tell you with 50% probability, I'm at the North Pole, and 50% probability, I'm at the South Pole. So that's like a quantum coin flip. And in fact, this operation is one way of actually getting equal superposition and getting you into a point where you can actually play like with the probability. Now, everything I've told you so far is probably going to be covered in about 15 minutes in the first lecture on real quantum computing. So we're not going to go any further into it. But the key thing to walk away from here is this. One, quantum computing is actually more closely related to classical than you probably knew. Effectively, if you abstract classical computing the same way, the operations that you have are very effectively analogous. And two, because now you have a greater number of operations that you can do, there must be an intuition somewhere that this should speed up certain types of things. And in some sense, that's really one of the key improvements of quantum algorithms is to take advantage of things like this. Now let me go back to the stenciling bit for just a minute. If you notice over here, the state of 3 bits actually requires you 2 to the 8 complex numbers to represent its state. And this should again give you a sense that there's a lot of information in the quantum system when you have 10 qubits or 15 qubits or 20 qubits or whatever it is. There seems to be a lot more information than you can possibly store. Because just like in the chess game with the dice, you run out of space fairly quickly. You can store about 30 qubits in about 16 gigabytes. And every 10 qubits you add basically makes your space requirement goes up by 1,000. And you hit a hard limit fairly quickly, which is when you hit about 250 or so quantum bits, there aren't enough atoms in the known universe for you to actually store, if you store all the complex numbers, right? Even if you store one complex number per atom, you couldn't actually do it. And this should give you a sense that there's something going on in here. Nature is using some more fundamental way of storing the information and manipulating it than we are with our top-level abstraction of everything's a 0 and a 1. And by throwing away that abstraction and using the more fundamental abstraction, you can potentially do a lot more in terms of compressing the data and being able to get a higher degree of parallelism. And in some sense, that is very loose definition of why quantum algorithms work better. Of course, for 260 quantum bits, that looks like a fairly small number. It turns out that you need 2 n bits to solve an n-bit RSA problem. So, to solve that 2048-bit number, just to write down the initial state, you'll need about 4,000 qubits. We still don't have one, so we're kind of still safe on that front, right? But then what does it mean to have a qubit? And are all qubits created equal? And the answer is no, because qubits are fundamentally, logical qubits hold their state forever because you write them down on a piece of paper, a large piece of paper, right? But real qubits, the ones that actually store the information quantum mechanically, they decohere very quickly because any interaction with the environment that the device is in counts as a measurement, and you lose information very quickly. And so the faster a qubit decoheres, the less chance you have of actually using it for computation. And so it matters whether you have a qubit that has a high error rate or a low error rate. And at the moment, the state of the art seems to be qubits that die in about 10 to the minus 5 in a second. And we can then start putting more and more of these qubits together to try and fabricate a logical error-corrected qubit. But then there is actually a cutoff point where it doesn't matter how many qubits you have. If the error is below a particular threshold, you won't be able to get a logical qubit out of it, even if you put 1 million qubits on it. A different approach to doing it is to try and get qubits that have a lower error rate. And when you do that, then when you add more qubits to the system, you can actually come up with a system that has more logical qubits. And in some sense, that's kind of the approach that we've been working on at Microsoft. So back in 1937, there was this Italian gentleman, Ettore Majorana, who hypothesized that there was a way of actually creating a quantum device that actually didn't store its information in a way that was easy to decohere. I'll give you an idea, just a general sense of what that looks like. So think about an electron, right? An electron has a spin, and a spin is in superposition, so it's not actually spinning up or down. It's sort of 70% up and 30% down. And if you can just hold on to one electron and you keep it in perfect isolation, well, maybe you have a qubit, right? You can now spin it and you can do all kinds of stuff with it. But that's not how nature works, because nature has got like billions of electrons all over the place. They're all spinning around however they feel like, and they're all interfering with each other, which means that the initial electron of interest that you had will lose its information fairly quickly, and you won't be able to actually use it properly. But one way of doing it, one way of sort of making this thing work, is to try and see if we can line up the electrons in a particular way so that all the electrons in the middle have their wiggle removed. So if you can line them up in some particular way, if you find a way of actually making that work, then you'll end up having just the information that you need in terms of the whole spin be delocalized between the front and the back end of that chain. And it turns out that we could actually do that. It turns out it's almost like making a fractional electron. And this piece I will just skip over. But the idea is that if you actually, under the right physical conditions, you can actually set up a chain of these things and then shift the chain a little bit so that the electron effectively appears half and half on two ends of a very long chain, which means that it's very difficult to destabilize such a system. And we actually glimpsed this in the lab in 2012. So this device actually exists. I mean, we actually have seen Majorana particles, and you can actually use Majorana particles to create a qubit and create a qubit of very high fidelity, at least in theory. The physics is somewhat more difficult. We actually have to create the devices now that exhibit the Majorana particles and actually use them for computation. That's the work that we're currently working on. So that segues nicely into what does a computer look like. So what will this quantum computation framework look like? Physically, that's just the fridge in which the device sits. Physically, because these quantum mechanical particles decohere so quickly and require so much isolation from their environment, the best way we know how to do it is to put it inside a heavily shielded chamber and chill it. And the closer you get to absolute zero, the less interference a particle will have with its neighbor. And so we get down to about 15 millikelvin, somewhere on that fridge. And we have a way now of actually interacting with that device. But obviously, the challenge of doing all of this is not just to get the device or get it down to 15 millikelvin or get wires in or whatever it is to actually convert this whole thing into a real computer. And logically, this is how we've dreamed it up. So we have if you want to think about the logical image of a quantum computer, it's like a coprocessor that lives on another machine that you're not likely to keep in your own house because you've got to have liquid helium to bring the thing down to 15 millikelvin. So we basically create the coprocessor, the quantum device, and ship whatever code needs to run on the coprocessor across to it, execute it, and give you back the results. And that's effectively the programming model that every quantum device that currently is being developed, that's the model that we're following. So obviously, from a language design perspective, if you think about what you're trying to do, you're trying to write a piece of code that does some computation. There's a complex bit of code that does really complex mathematics, which the coprocessor can do much faster than you can. So you need to find a way of expressing that computation sequence in a way that can be shifted off to the coprocessor. And now that is a little program in itself. So it makes sense to make that expressible in a type-safe way, in a way that you can reason over it, optimize it, in a way that you can actually start basically improving the handwritten code or shared libraries on it and so on and so forth, which is why we came up with QSHA, the language that is used to define sequences of quantum computations. Ultimately, at the moment, we have a simulator that you can run. You can have, 30 perfect qubits on your local device. Ultimately, there will be quantum hardware, and then the same code that you write now will actually run on the device. So in some sense, that initial slide where I showed you about the improvements that we made to the Femoco simulation, that code will actually run sometime. This was a language design slide. I was going to go over that, but I'm running short on time. So I'm going to move forward and show you a little demo. So this is the tool chain that is now available. We have a language, we have some dev tools, a simulator, and libraries that you can download. And I'm just going to take a look at this quantum weirdness thing, which is a good way to end the talk. So let me see if I can bring this up. Can everybody see that? No? This thing is not helping me because I don't know what I'm actually showing. How about now? Does that look okay? So what you've got there is a little program that basically has 3 functions. One, which is a Hadamard gate, that effectively is like a quantum coin flip. Another one has two Hadamards, one following another. And if you think about what that looks like in terms of your intuition for what happens when you flip a coin twice, the behavior is somewhat different. And then the third one is, I'm just going to observe the qubit between running the Hadamard twice. And let's just see what the behavior turns out to be. So let's see. So the first one, as I showed you, just puts it into superposition. The second one has two Hadamards one after another. What do you think happens when I put in a state? What do I get out at the other end? It turns out that this is a quantum coin flip that knows how to unflip itself. So if I start with a 0, I'll always get back a 0. It actually undoes the operation entirely predictably. So by just putting two Hadamards one after the other, even though the result halfway is unknown, the result at the end is always what it was when we started. And then third one is more interesting because all I'm doing to the qubit is observing it in the middle, and it actually interferes with the whole computation, and I will come back with equal chances. And I'm going to show you that, and that's actually going to be the end of my talk. So let me see if I can let's see if this works. This is not working. And everybody see that? And I think, so here's a single Hadamard, and I gave it false 1,000 times, and it came back with roughly 50-50. I gave it true 1,000 times, and it came back with 50-50, give or take. When I do that double Hadamard, when I give it false 1,000 times, I get back false 1,000 times. And same thing for true. And when I observe in the middle, I get the same behavior as I would expect from the single Hadamard. Now, this is running on a local simulator on my machine. It's just using standard linear algebra to do this stuff. So you can actually use the 30 ideal qubits to get a sense of the quantum mess and the quantum behavior and so on and so forth. You can't crack, RSA 2048 yet, and you never will be on my machine. But that's the idea. The idea is that the quantum mechanics of it is fairly straightforward from a mathematical perspective. The simulators available, there's tools, there's a language which is fairly easy to read and easy to write, and libraries that you can read. So you can get started on this stuff right away. So I'm going to end the talk there, and we see. And ask for questions or wrap up.
So let's give Don a round of applause.
Thank you.
And we have time for one question.
Hi. Thank you very much for your talk. I've just a question. We don't know yet whether quantum computing scales, right? I mean, there could be like decoherence, which makes it difficult. There could be a law of nature. I mean, we don't know. So in a way, building a quantum computer is an experiment, but in the end, we never know the result of an experiment until we have done it, right?
Sure, that's a fair point. I mean, from a mathematical perspective, there's no reason why we can't tensor 260 qubits together. Whether there's a physical limitation that actually comes up, we don't know yet. It's very much in the preliminary stages of the science. But the math is pretty sound, and it's actually quite comforting to see that if you frame it in the right light, it doesn't really violate classical computing from that perspective. Yeah.
So I know there are more questions, but we run out of time, so
Yeah,
please don't
Simon,
hesitate
come by
to
and talk.
ask John questions outside.
Cheers. Thank you so much.